play a role. So I want to review and perhaps even say some things about open questions in the field of gravity capillary solitary waves and lumps, which are like fully locally confined solitary waves. This has been going on, this work, for some time. In fact, I'm old enough to have been in previous water meeting here, I think 2001, and at that time, one of the dominant participants was Michael Longet-Higgins, who I think is still alive, right?
Yes. His office is next to mine.
He must be 90 years old, according to
He
mine.
just gave a talk, though, a couple of weeks ago.
Oh, he did?
Yeah.
Oh, very good, very good. He must be 90 because it's the same generation of Lighthill and Dyson and Longet-Higgins. All these were classmates at Cambridge. I don't know about Dyson. Longet-Higgins and Lighthill don't have PhDs, as far as I know. But that doesn't matter, of course. And they were, I think, 1924, so he must be 90. I'm not positive, but I'm willing to bet on it. Anyway, he was one of the dominant speakers, and this was an emerging subject at that time. In fact, it would be interesting to see what happens in these 13 years. And now it's more of a mature, but they're still open questions. So it's an interesting way to look at things and how meetings like this can help in making progress, even in very traditional fields as waterways. So as far as I'm concerned, from my own point of view, listed here some collaborators over the years, Frederick Diaz at the beginning, and Roger Grimshaw most recently with Jim Duncan, who's an experimentalist at Maryland, and here are some students, graduate students who did PhD with me over the years. This is a very brief outline of what I'm going to talk about. First of all, this idea with the solitary waves and lumps has helped us understand in general terms how solitary waves and lumps may arise. And when I say this in a way that how they arise, how they bifurcate from infinitesimal waves. So that's a more precise way to put it. Of course, there are different regimes, the shallow water that Harvey touched on. Of course, the other regime where I'm going to focus more is the finite or infinite depth, pure gravity versus gravity capillary, 2D versus 3D, and purely inviscid versus viscous. This comes into play here. The idea of viscosity is much more important for the scales I'm talking about. Another thing which goes together with this bifurcation idea is that the critical speeds at which solitary waves can bifurcate from infinitesimal waves are also critical speeds for the force response. If you have a moving forcing, like a pressure distribution, and therefore the two go together, and therefore, because there is resonance in that case, I will explain that a little bit more, the solitary waves and the lumps do play a role. So the two subjects you can talk about together, and it's very useful. I'm going to talk then about how one can use this forcing idea, the idea of using the force response to generate lumps. As far as I know, this is the first time this was done in the laboratory. And these show a remarkable interplay between dispersive, nonlinear, and viscous effects. We need all three of them. In fact, here the forcing is also a device by which you can overcome the viscous effects. And that's what allows you to generate those lumps in the laboratory. I'm going then to talk a little bit about the comparison with the model equation, which in some ways is ad hoc, but it does have some predictive power and summary conclusions in it. I will touch on some open questions from my point of view, at least. So here is bifurcation of solitary waves and lumps. The classical problem of water waves with surface tension and gravity, the familiar dispersion relation that includes both gravity and surface tension, And the result is a very remarkable and simple result. I wonder why this has not been done over the centuries, is that the solitary waves and lumps may bifurcate from linear waves. If you look at the linear spectrum, which is the phase speed as a function of wave number, here we have the frequency as a function of wave number. The critical speed at which you can have bifurcation are the extrema of the phase speed. And physically, the important idea there is that you can show that from simple calculus, that the phase velocity is equal to the group velocity. And that's crucial for generating small amplitude solitary waves and lumps, which can be continued, of course, by numerical methods or other approaches. Now, if we take this condition a little further, you will see that in the water wave problem, you can satisfy this condition in two different ways or in two different regimes. One is the classical shallow water limit, because in that case, you have either a maximum or a minimum of the phase speed. Usually you have a maximum, a minimum you have to have a lot of surface tension. But that's one possibility for very long waves, in finite depth, obviously. The other case is the case where you can have such an extremum. Of course, here the extremum happens strictly at the zero wave number, that is extremely long waves. Here the extremum for finite or infinite depth can happen at a finite wave number. So you're bifurcating from a finite wavelength wave train, but the bond number, which measures surface tension relative to gravity, has to be less than 1/3. Physically, the difference for that is that, of course, you always have an extremum at the zero wave number. Now, if the bond number is less than 1/3, you have a maximum at the zero wave number, then the phase velocity goes down, has a minimum at the finite wave number, and then goes up because of surface tension effects. So this is why you need that. Otherwise, you don't have that extra minimum of the phase speed there, and that's why you cannot have these solitary waves, just from a kinematic point of view. Now, as Harvey, of course, mentioned, and he showed Cordovec, you showed Cordovec, right? Not De Vries, okay? The shallow water limit has been studied for a long time, and centuries and so on. The interest on the second possibility here is, I would say, exactly 25 years old. I think it was Longet-Higgins who first published numerical evidence that you can have solitary waves on deep water if you put both surface tension and gravity. And that, I think, was 89, if I'm right. So I would say almost equal to last 25 years. And the main players, or some of the older players, and of course their students and collaborators, I have listed here, starting with Longet-Higgins' early numerical work. There's also a review article that Roger Grimshaw did a few years ago, one of the chapters in this volume, Solitary Waves. Okay, so obviously I'm going to focus on this less studied regime.
Excuse me.
But before, yes.
The condition you wrote down, that group speed equals phase speed, that's also the same condition for second harmonic resonance, isn't it?
No, second harmonic resonance, I think the phase speed of 2K has to be the same phase speed as K. Kinematically, same idea, but
it has
different.
to do with the minimum.
Yeah,
Okay.
but it is a different, yeah. Okay, so, but before going to the finite or infinite depth situation, let me summarize in this slide everything you needed to know about bifurcation of solitary waves and lumps in shallow water. I don't know if you were afraid to ask, but this is everything you need to know. Very briefly, we have possibilities of gravity only, gravity and surface tension, but the bond number less than 1/3, which is sometimes they refer to as the light surface tension, strong surface tension, gravity, the bond number exceeding 1/3. The reason I put this slide is because it shows a story, which also is the same story also in infinite or finite or infinite depth. So let's go over it briefly. If you consider gravity only, which is what Harvey talked about, The extremum of the phase speed is a maximum. The one-dimensional evolution equation for waves moving in one direction is the KdV. The solitary waves have a set-square profile. They're stable to transverse perturbations. The Kp equation is the so-called Kp2. This has to do with the relative sign of the dispersive term, which corresponds to this maximum here. Are there lumps? No, there are no lumps because the solitary waves are stable to transverse perturbations. If you put some surface tension, but the bond number is less than 1/3, the extremum at the zero wave number is still a maximum. The KdV holds. However, the solitary waves are now not locally confined. They have small oscillatory tails because, as I told you, the phase speed starts from a maximum at k equals 0, goes down at the finite wave number, and then goes up. The solitary waves of the KdV type have a phase speed which is a little bit above, outside the linear spectrum, but it interacts resonantly with a finite wave number which has the same phase speed, and that gives rise to these tails. Lots of work on that. You can do exponential asymptotics and that in numerical work. So that's how you find the generalized tails. They play a role actually in internal waves, they're in measurements and so on. So they explain some things, but in a different context. In that case, the oscillatory tails are of a lower mode than the main solitary wave, but that's an aside. The transverse perturbations are stable, same Kp2, there are no lumps. The large surface tension situation is interesting theoretically because then the extremum of the phase speed at k equals 0 is a minimum. The KdV still applies. You can still have set-square solitary waves, but now they're of depression because the minimum at k equals 0 is a minimum. You have to move with a less speed, of course, to be outside the linear spectrum. You have nothing to resonate with, so set-square with a negative sign. Transverse perturbation is now unstable. In this case, you have a minimum of the phase speed, unstable, Kp1, and you do have lumps. These lumps, very interesting theoretically. I don't think they have been ever observed in experiment, and the reason probably is because if you go back and put numbers to this bond number greater than 1/3, the depth of the water is on the order of millimeters, viscosity and so on. This is very, very difficult to do. But there's a lot of interesting theory. So I want now to move to the case I'm interested in.
Can I ask a question?
Yes.
In that previous list, in the solitary wave row, bond number less than 1/3,
Yeah.
Couldn't you also get Kawahara?
Say that again?
Could you also get Kawahara?
Yes, there are many versions of KdV where you add an additional term to generate the minimum. You can do that. Theoretically interesting. It's not the real water waves though, because the real water waves is way out the resonate wave number. The Kawahara is when the bond number is close to 1/3 and slightly less. So, if you want to be accurate, you have to be close to 1/3 to use Kawahara. Yeah, you want fifth order KdV. This is the same thing. Yeah, sometimes they call that fifth order KdV. Yeah. Okay, so now I want to go to what I'm interested in, which is solitary waves and lumps in the finite or infinite depth, and you will see the story. If you know the story for shallow water, this is not unexpected what you find here. And here, before giving you any details, I have summarized the results of the most important bullets here in bullet form. Well, as we said, as we said here, both gravity and surface tension must be present, and a bond number has to be less than 1/3. The extremum of the phase speed at finite wave number is always a minimum. Okay, so if you have solitary waves or lumps, they have to move at a speed less than that, so you're outside the linear spectrum. Okay. Now, close to the bifurcation, which means close to this minimum, you can have small amplitude solitary waves, but now the physics is a little bit different. But because the phase speed is equal to the group speed exactly at the bifurcation point, these are really wave packets whose envelope and crests move at the same speed. So they're really solitary waves, but of a different nature. In the other case, you have long waves, so there's no envelope and carrier. Here we have envelope and carrier, but they move with the same speed, so you can find branches of solitary waves that can bifurcate from there. This was the first time it was done analytically in this form. You can use the NLS in 1D, and the 1D envelope equation is the NLS, and the envelope in that case has a search profile. You can show analytically from the NLS that you can have two branches of solitary waves, one elevation corresponding to a maximum of the envelope, or the maximum of the envelope coinciding with the crest or with the trough, so you have elevation or depression. There are two different branches, but it's much more subtle than that. You can slide the envelope relative to the carrier, and you can have an infinite number of solutions, and you can use exponential asymptotics, and you can do all kinds of things. This was the thing we talked about with Longet-Higgins at that time. Longet-Higgins was, and still is, an extremely smart guy, but what is remarkable about him is that he always does absolutely what's necessary, no more than that, and if he needs to learn more, he needs more, and he does whatever is necessary. At that time, when I talked about that, he had not thought about the possibility of sliding the envelope relative to the carrier, so we argued a little bit. We left it open. Then during dinner, at dinner time, there was some kind of banquet here. I see him with volumes of JFM. He had come to JFM. He brought the volumes to explain to me where he was coming from, and so on. I thought this was remarkable because he was, in his late 70s at that time, and this shows really genuine interest of somebody so important like him. So anyway, this is a fascinating topic from a theoretical point of view. What is more interesting is that the transverse perturbations are always unstable. If transverse perturbations are always unstable, you expect lumps. 13 years ago, we didn't know anything about lumps, so this was all 1D at that time.
There's a question over there.
Yes, I'm sorry. Yeah.
So in the NLS model, the carrier wave speed depends on the amplitude, but
Yes.
the envelope speed does not depend on
Yeah.
the amplitude. So
Yeah.
how can the two velocity be equal?
You can perturb the carrier wave number a little bit, and that's how you generate the two branches of solitary waves that bifurcate. What you're saying is absolutely correct, but you perturb the carrier. You have that freedom, and you can match the two, taking into account what you said exactly, that the phase speed of the carrier depends on amplitude. That's how they bifurcate, yeah. Okay, so if we move now to lumps, which is more recent stuff after the previous water wave meeting at Newton, well, if you work in the same way like NLS, you can derive a two-dimensional envelope equation that is, well, it's sort of like a Davis-Stewartson thing. More accurately, is the elliptic Benny Roski's Davis-Stewartson version. I'm not going to go into this. Benny and Roski derived it before Davis-Stewartson, but that's okay. One appeared in Studies in Applied Math, the other appears probably in Proceedings of Royal Society. That's why it's more often quoted. Now this has a solution which is locally confined, which is called the Towns envelope. That was found first in optics by Towns, and this is interesting because this is the borderline between what is called between collapse and non-collapse. That is, if your initial envelope, in some sense, is below that, is less nonlinear, then it will disperse out. If it's above that, then you have nonlinear focusing, and you have wave collapse within that equation, of course. That doesn't mean everything collapses. However, from our point of view, if we go back to the physical problem we're interested in, the situation is that away from bifurcation, that is, if you move a little bit away from the critical speed, all these models, the NLS and the BRADS and all these, they quickly become invalid because the idea of the separation of envelope and carrier is immediately lost. So you don't have that structure anymore to a good approximation. And also, the effects of viscosity cannot be safely ignored if you want to have any connection with reality. There's tremendous room for interesting theory, but don't expect the viscosity to be really ignored. So to give you an idea, here are some computations of these lumps in this close to bifurcation. You see they look like, you can see the envelope and the carrier, and this cross section, you can see the nice, this center line, you can see the nice envelope and carrier and so on. But if you go a little bit away, then it becomes a lump of depression here, and this is the cross section, and as you can see, there's no idea of, there's no envelope and carrier, they just have one trough, and so the whole approximation fails. Okay, now let me shift gears and show you how this is also interesting from a force point of view, and this also provides a resolution as to how one might observe these lumps, since viscosity is so important here. All right, so the other thing here is that the extrema of the phase speed, which are the bifurcation points for solitary waves and lumps, are also critical speeds when you have forced response, like you have, let's say, here a pressure distribution which moves with speed v, it's externally provided, it moves with speed v, you want to find the response. This is a classical problem, you can find in Lamb and Whittam and so on. But the interesting thing is that when the speed v is equal to this critical speed, the steady state forced response is singular in the sense that the unsteady response grows with time. The reason for this physically is pretty clear, because the phase speed is equal to the group speed, and therefore the energy cannot move away from the forcing because v is equal to the minimum speed, you have resonance. This is the resonance in wave problems, all right? The analog of the simple harmonic oscillator, which you oscillate and get resonance. This is the analog of the resonance for water waves. You have to introduce the idea of group velocity, which tells you what happens to energy. Okay, now, so it grows with time. Now, in the KdV case, in the shallow water, it grows with time actually like t to the 1/3, because you also have a little bit of dispersion, so it's not like t in the simple harmonic oscillator, but it grows in time. If you're a fixed point, it grows like t to the 1/3. In the case of finite wave number, the growth is very mild, is only logarithmic, but it's still there. This, in some sense, from a theoretical point of view, is a bit disappointing if it's logarithmic. Probably you think it's going to be masked by other effects, particularly, of course, viscous effects, and therefore nonlinear effects may or may not become important for transcritical speeds, at least for the case of finite wave number. Okay, well, let's see what the story is. Now, in shallow water, the force response, this was something that was done when I was in my early faculty years, good 30-some years ago, believe it or not. And the whole idea centers around the force KdV and the periodic shedding of KdV solvents. That is, the resonance in this time, because linear waves cannot radiate energy, nonlinearity comes in and gives you a resolution, and energy is being radiated out in the form of solitary waves, which will go upstream, of course, because they move faster than linear waves. So this is all well known. So the question then is, what happens when we have solitary waves at a finite wave number? So let's say at the minimum phase speed for bond number less than 1/3. So we expect to see what is the role. As I said, from as a first guess, you may think the role is not going to be there because of this logarithmic growth and because of viscosity. The other bad thing here, from a theoretical point of view, is that the weakly nonlinear approach, which is based on model equations, is very, very limited. Also because of viscosity, but also because you don't have envelope anymore. So all these are things to take into account. Just as a very, very brief aside, in addition to water waves, of course, you can do similar things with interfacial waves at minima of the phase speed. And also another topic, I will come back to it very briefly, is the possibility of using, instead of capillarity, using flexural waves by putting a flexible plate, elastic plate on top of water, and there have been attempts in this way theoretically. I'll make more comments about that. So again, the basic ingredient, of course, is the minimum of the phase speed. Okay, now, just to tell you now, before giving you any theory, I will tell you some, I will summarize some experiments that were done by Jim Duncan and Jamie Diorio at the University of Maryland. And before I say this, Longet Higgins, together with Sang, also tried to do some experiments for the solitary wave because they didn't know it was unstable to transverse perturbations at that time. This was a little before the 2001 meeting. This experiment was very unsuccessful. Shouldn't say, inconclusive is the better word. It's not clear what this was doing. But here's the arrangement that Jim Duncan is a virtuoso in water wave experiments, particularly breaking waves, extremely talented. What he did, he had a carriage here, which was moving from right to left in the traditional British way, instead of left to right. And he was forcing air, there was compressed air through a little nozzle here. This was the forcing, moving with speed v. This is water, essentially deep water, and the minimum phase speed in this case corresponds to 23 centimeters per second. The forcing parameter, the strength of the forcing, the way he defined well called epsilon, it's the ratio of two length scales. It's the ratio of the depth of the depression which is created by the air forcing. If this is stationary and you just force air, you will generate a little bit of a depression there. It will have a certain depth of a few millimeters. Now, if you divide this by d, which is the diameter of the hole of this nozzle here, which is 2.5 millimeters, that gives you the epsilon. All right? And the speed parameter is, of course, the ratio of the speed of the forcing to the minimum phase speed. So alpha equals 1 is the critical speed according to linear theory. So here is what happens. This summarizes the four states which are seen experimentally. There is a subcritical state which corresponds to subcritical speed. So alpha is 0.905, so it's a little bit less than the 23 centimeters per second, about 10% less. And you can see it's essentially a depression under the moving nozzle here from right to left, and we call that state 1. That's the linear response. If you put something in steady state, it moves. Now, many things happen within a very narrow range of speeds. This is very remarkable.
What is the fluid?
Water.
Water.
Water. So this is a real thing. It's,
Okay, so what is the Reynolds number?
I don't know. You have to tell me how to explain. But
We have a wave speed. You have the kinematic viscosity.
you can, yeah, you can do that.
You
You can
said
do.
the depth is only a couple millimeters.
It's about 200.
No. A couple of millimeters in.
100 to 100.
Okay,
I
so
think.
It's about
really-
100.
really
About
business.
100.
No. A couple of millimeters is in the shallow water.
Oh,
Here,
right.
here is deep water.
Oh.
We have changed gears. Yeah. I'm not going to report experiments of that other regime. I'll leave that to others. I'm not an
Are there any
experimentalist.
experiments in the shallow one?
Nobody has done.
Oh, I see.
Yes.
Can you give an idea about the scale?
Yes.
Yeah.
As I said, the diameter of this nozzle here, if you go back, the diameter is 2.5 millimeters here. So we're talking very small stuff. It's about 2.5 millimeters the diameter of the thing here.
So the hole is also 2.5 meters.
Yeah. So
Do you know if Jim is willing to do this in mercury?
that's a very dangerous fluid.
Because the Reynolds number goes up by a factor of 10.
I have to ask him. I cannot put words into his mouth. That's a very dangerous fluid too. You know, you have to take insurance. Insurance is going to cost you.
So, actually, in the other regime that you were talking about, there was an experiment done in mercury.
Oh, really? Okay.
Yeah, right.
So it has been okay.
Yeah, and
mercury, okay.
there's been a shallow water experiment.
I
with
see.
mercury.
I see.
So they were using it to show the depression solitary wave in KDV.
Okay. All right. I'm good. I didn't know that. Okay. I didn't. Okay. So let's. So here is the states. So as I said, many things are happening within a very narrow range of speeds. This is 90% of the critical speed. This is 97%. You can see now that here is the moving forcing. You have the depression under it, which is not too different from this. But in addition, you have what appears to be a lump behind it, which is still connected though. Still connected. This is a steady state, which is moving with the forcing. So it's like having a lump which is steady. It is connected because if it were not connected and receiving energy from the forcing, very quickly it dies, as we're going to see, gets dissipated. So it's a very interesting situation. You have what appears to be a steady lump behind the forcing. Then, if you go to 98% of the critical speed, this steady state becomes unsteady, and you start shedding lumps. I'm going to show this much more clearly later. This would cause state 3. So you apparently have some kind of a bifurcation, like a Hopf bifurcation from a steady state to a periodic state where you shed lumps here periodically, which very quickly, of course, get damped. As soon as they lose touch with the forcing, where they get their energy from, they just dissipate out. And then finally, when you go to over the critical speed, then you form a new steady solution, a new steady pattern, which is essentially the ship wave pattern in this kind of situation. So within a very narrow range of speeds, you have very interesting dynamics which is happening, even though we do have viscosity here. Viscosity of the Reynolds number is 100, is, well, it's not small, but it's not huge either. And also, as I said, the linear theory gives you only logarithmic growth of the unsteady response at critical speed. So it's a very interesting situation. This slide shows in more detail the time history of the periodic response, which you can see here. This is the beginning of the cycle. You have the two lumps which are forming. They keep moving away. Here they moved away and they have damped. They have damped more here, and then you start again. This is pretty much the same as the original. So this is the whole cycle. In terms of times, we're talking fractions of a second, the delta t. So the whole thing, it takes a couple of seconds to do. So this is a very fast, very different. It's not the 20 minutes of the wave going up. So we're in the other things are happening fast here. Okay, so if you do a response diagram where you plot the maximum depression as a function of the forcing speed, you have a typical nonlinear oscillator situation. You have a state 1 here as you vary the speed. Here's the critical speed. Subcritical, you have state 1, which is you can characterize here. Then state 2, there's a jump, very characteristic of these nonlinear problems. There is a jump, and you have here is the lump, because this is the maximum depression now. So this is where it is, that's state 2, and which is steady. And then you have, this is a new bifurcation here, and then state 3 is oscillatory periodic, and then you go back to steady state. And another interesting thing here, which is very important physically, is that if you do this experiment for various forcing amplitudes, so from weak forcing to moderate, stronger, and very strong forcing, of course the linear response varies linearly with amplitude, so it goes up as the amplitude goes up. But if you look at the state 2, which we claim has to do something with the inviscid lumps, state 2, all the data pretty much collapse on the same line, because essentially we're plotting here amplitude as a function of speed. That's a nonlinear dispersion relation, and you can see the data collapse very nicely on the same line, indicating that there may be something going on. And then here we go the state 3. Okay? Now, very, very briefly, a nonlinear model equation, which is unlike the KdV and the NLS and the Kp and all these are all model equations which are derived not rationally from the equations of motion. Asymptotically, this has ad hoc elements because we're dealing with really a nonlinear phenomenon, which is 3D, unsteady, potentially unsteady, and also, of course, viscosity is important. So everything is there in the problem. There's really nothing we can get rid of, or almost nothing. So here's the situation. We have a moving pressure source which moves again from right to left. Deep water, surface tension, and of course gravity plays a role. If you look at the dispersion relation in deep water, that's how it looks. You can non-dimensionalize things such that the minimum speed is 1 when the wave number is 1 and 0, 0 in the transverse direction. So the minimum speed is, corresponds with only in the x direction wave number. And this is how the dispersion relation looks at that non-dimensionalization. The theory is very simple-minded. In a sense, it's same spirit as what you call the Witten equation, which, if I remember correctly, you take all the dispersive terms and a quadratic nonlinearity, and he wanted to see how peaking and breaking. There's no theoretical basis for that. It's just curiosity, and let's see what happens. This is pretty much what's going on here. That is, this is based on a second-order Taylor approximation close to the critical wave number, which is k equals 1, near minimum, but you don't make any envelope assumption. You just keep the dispersion relation as is. The viscous dissipation, we're going to use a linear viscous dissipation as described in Lamb's book. Quadratic nonlinearity, which is the simplest thing you can do, but match to the full water wave problem for the NLS in the small amplitude limit, and a Gaussian forcing, that's a natural thing to do. If you put everything together, this is the evolution equation you're looking at, and this was actually first proposed by Akers and Paul here in 2009 without the forcing and the damping, all right, which again you can add very easily. And this is pretty much the theoretical basis. This is the unsteady term. This is the viscous term. This is the nonlinear. This is the term that shows you how much away you're from critical speed. This is the dispersive term. It has a Hilbert transform because of the absolute values of wave number. This is the nonlinear term with the parameter beta, which is fixed, as I said here. And this is the forcing term. So that's all there is to it. Now, in terms, viscosity plays a key role here, and one has to be very, very careful, because as shown by Longet-Higgins, now it's 97, this was again before he was talking about solitary waves. The viscosity depends, actually, if the amplitude goes up, viscosity also changes. In particular, he shows theoretically that if you take weakly nonlinear solitary waves, then the coefficient here, which is sort of like an inverse Reynolds number, is twice what you would get for linear waves. So this is the linear law of decay. It's proportional to the square of the wave number, and this mu naught, this in dimensionless form, happens to be this. This is all linear water wave theory. If you go to weakly nonlinear solitary waves, which are packets, then you get twice that. This was done by Longet-Higgins. So it's a very complicated situation, and if you go to more nonlinear waves, then the damping is stronger. So what we're going to do is we're going to treat here mu as a parameter, but keep still the linear law of damping. This is all ad hoc.
What's the numerator of that?
Where?
V0 equals what?
Or no, that's mu 0. That's the dimensionless, that's like an inverse Reynolds number.
What's the numerator?
This is the kinematic viscosity of water and all that. So, which answers your question about the Reynolds number. Yeah. Okay, so this is the unsteady equation. You can do analysis with this. I'm not going to bore you too much, and I don't want to take more than my time. The key element here is that in an ad hoc way, we used as this inverse Reynolds number 2.4 times the linear one. The 2, you can, if it's weakly nonlinear, twice. It's going to be a little bit more. And the reason we use that is because we can match the first transition speed, where you go from the state 1 to state 2, and if we use this, and also the state 2 is steady state as observed in the experiment. So there's a little bit of fitting here. There's a little bit of fitting, but this number is not unreasonable, given that theoretically it's twice mu naught for weakly nonlinear response. Now, if you want to compare with the between the experiment and the theory, here I have the experiment. This is state 1. Remember, nothing is happening, just under the moving forcing. You have a depression. This is the numerics again, and it shows you here the millimeters and all that. So this is all steady. If you go to state 2, this is again 97% of the critical speed. This is the experiment I showed you before. So you have something under the nozzle, and you have what I'm going to, I hope to convince you it's a lump behind. Again, here, this is what you see, and you see something forming behind, which looks qualitatively. Here, we move to state 3, which is the unsteady, and you see the lumps which are shedding out. This is one snapshot. The lumps are shedding out. I'll show you the full cycle in the next slide. This is shown here, and you can see the cycle here experimentally, the lumps which go here and they move away more, and they get damped. And then it starts again. And if you look at the theory, you see here, looking from the top, you see 2 lumps here being close to the forcing. Then they move away. As you can see, they get damped, and 2 new ones start forming here, and then move away, and then pretty much is the same as the beginning. So we have a cyclic phenomenon, which qualitatively is like in the experiment. And this is the state 4, which is the ship wave problem, a new steady state for supercritical speeds. In terms of the response diagram, we get similar response diagram with the theory for this ad hoc model equation. Here's the linear response. You have a jump, and then you have this nonlinear state 2 situation, similar here, and then you have the state 3, which is unsteady here. You can also, theoretically, you can talk about this problem by a steady state bifurcation analysis, where you drop the unsteady term and you look at possible steady states. This is revealing. This is also a situation where you can do some analysis. As a typical nonlinear problem, you expect multiple solutions for a given speed. That's also suggested by the jumps you see experimentally, and also by the numerical simulations. This is a problem where you can do actually perturbation theory, but you have to be careful what you use as your base state. The way to do perturbation here, or the way we found convenient, is your base state to be a free solitary wave or a free lump, which you perturb by slight forcing and slight damping. So you use the damping and forcing as your small perturbations, and you do perturbation theory that way. This is very revealing, as I'm going to show you in the next slide. This is the bifurcation diagram you get. So we're plotting maximum depression here as a function of speed, and this is the linear response. And in the typical nonlinear fashion, you have a folding point, turning point, and then you go up, and you have some funny stuff going on here, and then you come down, and actually there's another turning point here, and you go up, and you can keep going here. There's interesting, but physically, it doesn't really matter. It doesn't really, because these are unsteady, the states, these are never attained. Now, so as you can see, we have multiple solutions for a given speed, and there are several turning points, and the interplay between nonlinearity and dissipation is obvious. If you don't put dissipation, you get this turning point here, but you keep going here forever, you never come back, all right? So this plays a role. So I can show you here pictorially what happens. So we have here, I marked various points as we go along this bifurcation diagram. So you see the first one here is essentially, as you can see here, here is the forcing, the position of the force. You can see the response is pretty much under the forcing. If you keep going, essentially it's under the forcing, doesn't change too much, although you start seeing some shift here to go a little bit downstream. And if you go up, after the folding point here, you see now the main disturbance is behind the forcing, all right? And you keep doing, and you see all these are now going, you see what happens? The disturbance is behind, sort of like a lump, and the forcing is here where the line is looking from the top, yeah? So, and then you see here, and that's where we are. Okay, so in terms of steady response. So the critical speeds are, of course, this alpha 1 where you get the first folding, and then the alpha 3 where you get the second folding here. It's within this region where you see the state 2, which is basically a lump just behind the forcing this way, because these states here are all unstable, because you go to the linear state, essentially linear state, this is stable, this is unstable, and it's in this region here where you see this lump here, all right? So, these, by perturbation methods, you can find this shift, you can predict this shift, so you can do a lot of this by perturbation methods, really, although this is numerical. So this state 1, state 2, as I told you, and this shows you the time histories. And if you compare with the experiment, this is more interesting now. As I told you before, for various forcing experimentally, of course, in the linear regime here for speeds which are subcritical, if you increase the forcing, then the response increases in proportion, pretty much. Then you have the jump, and you go into a state 2 where all the data collapse to essentially the same line for various different forcings we had here. As you can see, the forcing is doubled we have. Now, if you go into also into the numerical work, the theoretical work, the same thing happens. Now, if you try to see what is this line, well, this line is really the nonlinear dispersion relation. That is, if you were going to compute lumps and you plotted the maximum depression as a function of speed, and you start here from 0, amplitude would be, of course, implicit, and you go up here, this is pretty much very close to the dispersion relation for free lumps. So the interpretation of what you see behind is essentially a free lump, which gets enough energy from the forcing to overcome the very strong damping that you have. All right, so this is really, so you need the forcing, because you have the damping, you need the forcing to counteract that. So as a summary and conclusions, this took a little longer than I thought. I think you will agree with me that there is a very rich structure of gravity capillary lumps, perhaps remarkably rich structure on water of finite or infinite depth for bond number less than 1/3. And the dynamics is very interesting, but very challenging too, because you have basically all the ingredients there. There's nothing pretty much you can get rid of. 3 defects, fully nonlinear, viscous, and of course the dynamics sometimes unsteady. The lumps, again, surprisingly play an important part in the force response near the critical speed, even though the failure of the linear theory there is only logarithmic. So the resonance is very weak. Nevertheless, the lumps play a role. We have an interesting situation where the force response is very important in helping us observe these lumps, because it allows us forcing to overcome the damping effects and allows us to observe these lumps experimentally. And there is a reasonable agreement between the observation and predictions of a simple ad hoc model equation. Now, in terms of open questions, I know some of these are being now, I know many people are thinking about these. I think you can divide these into three categories. The theoretical ones, these are the ones which focus on lumps, with or without viscosity. Without viscosity, it's even more interesting. Theoretically, you can do more things. But I think one question is, what is the role of the lumps in the general 3D Euler equations? If you put initial disturbance with the right scales, of course, in the gravity capillary regimes, are you going to get lumps? What is the role of lumps? Assuming, of course, viscosity is not there. The detailed investigation of the collapse. We looked at that in some model equations. The lumps do play a role, and with the inviscid approximation at least. What is that role? Can you do that with the 3D Euler equations? Can you do it with other model equations in a reliable way? I don't know. We have indications that there are multi-lump responses. Some of the things I told you that in the steady bifurcation diagram will go up and down, and you can have multi-lump responses. Probably these are unstable, but interesting theoretically. So these are also important questions. Now, there are modeling questions. From a more pragmatic point of view, can you find reliable models without having to do the full Navier-Stokes equations, 3D nonlinear with a free surface, everything is there. Can you find robust 3D unsteady nonlinear models, including viscous effects, and also keeping in mind that viscosity is really affected by nonlinearity? I know Paul and his group have been looking into this with some successes there. So this is an important issue if you want to avoid working with a full Navier-Stokes. And now physical, the obvious question in my mind, when we want to sell this work, I didn't do it though today, was to say that these lumps are relevant to ripple generation by wind. The reason for this is that Zhang, who's an experimentalist at UCSD, Longet Higgins approached him to do some experiments way back on wind ripple generation by wind. And it's a JFM paper, and they show some profiles of ripples which they compare to profiles of solitary waves. Nothing was known about lumps at that time. Of course, the waves have finite extent in the transverse direction. These could be lumps, and we have all mentioned it in our talks in some way or another. I think this could be settled. In my opinion, this is tough because the experiments done by Duncan suggest that to generate lumps, it's a very delicate process. It's a cute little thing, but very, very delicate, between 0.97 and 0.98, and it changes. Now, can you do it? I don't know, but it's something I think has to be settled either positively or negatively. And then the other question which relates to some of these elastic gravity waves and experiments in reduced gravity and so on, can we find other models or other situations where this mechanism, the same physics, involves larger scales, and in which case it would be more easy to visualize and also maybe even more practical. So I would like to end with that, and I'll be happy to try to answer questions.
What about for steep Stokes waves, where we have a pressure disturbance due to the curvature at the crest? Is there any reason to believe why we would or would not see these types of lumps?
You mean little ripples on top of the
Well, if
steep?
you go back to Longet-Higgins' 60 right, it's the fishing line problem.
Yeah.
So if we think about the extension of that model to something more nonlinear, do you expect to see the phenomena that you've been describing?
I'm not, to be honest, I'm not sure if we're talking about the same thing. You have to have a forcing which moves very close to the minimum phase speed. If you don't have that, you're not going to see them, and I don't think that's the case there. So,
What sort of a Stokes, or what sort of a size Stokes wave are you talking
I'm sorry?
about? No, I'll ask
Oh,
again.
okay. All right.
I would add one question. I think in shallow water,
Yeah, you're talking about the very shallow.
yeah, very shallow water,
Yeah.
you can also see these guys because I claim to see them on the beach in Rio. Okay, and the reason is
Only in
because the
Rio?
sand is very fine, and what is playing the role of forcing is the fact that gravity is actually keeping the flow going down, and you can see little dimples form
Yeah.
by a grain of sand or something by a seashell, and these things are not vortices because you can tell that they're not vortices from the way they are, and they propagate for a little while and then they dissipate. And so I think that an additional interesting mathematical question is how to connect the deep water to the shallow water one with viscosity, with this damping and gravity, because then it sort of connects the whole.
Yeah, okay, I agree, and you can add it to the list.
For shallow water on the beach, you have also strong shear.
There's strong shear, too.
And this is a completely different family of solutions.
Yes, there is the shear. I mean, there's obviously the thin film equation, right, which gives you which comes from the shear. But the thin film equations has the same field as this. I mean, if you add strong surface tension, you get
But it's
Yeah.
complicated.
yeah, it's more complicated.
Yes,
Yeah, but I'm sorry, just going back on it. If on a deep water, there would be generally a very large vortex around the crest. It will actually try to topple them. Whether that,
Oh
I mean, you said something about the shallow water. That's what you've seen.
no. In the shallow water, these things are because I mean, when you have shallow water flow around seashells and things like that, you can get vortex shedding, which gives a surface dimple. That's all.
Oh, I see.
That's all. But those are not that.
No,
Because
no.
you can
yes,
Your colleague John Bush talks about these insects that walk on water, and they generate little surface tension depending patterns on the water, which look very localized. Is there any connection there?
I don't know. Are these insects programmed to move at 23 centimeters per second? Then this all suggests this is a cute, interesting, but specialized.
Evolution is a great optimizer. Okay, well, I have one quick question. Since
Yeah.
I'm the chair, I
Yeah.
have the liberty of asking a question.
Yeah, sure, of course.
You concentrate on solitary waves that go to zero,
Mm.
infinity. Have you thought about ones that don't go to zero, like go to periodic states? More interestingly, in 3 dimensions, in 2 horizontal dimensions. Because in 1 dimension, we know about dark solitary waves, for example, but in more than 1 horizontal space dimension.
The answer is no, but I think if you start dropping the requirement of zero at infinity, then I think you're not even restricted to moving at speed below the minimum, so you're outside the linear spectrum. Because this is what makes a solitary wave. You move outside the linear spectrum, so you don't resonate, you don't carry any waves with you. So I think it's a different ballgame now, and I'm not.
Okay, well,
What is the physical origin of the nonlinear, the factor of 2 in the viscosity?
I'm sorry,
The physical origin of the factor of 2 in the viscosity that in the weakly nonlinear regime. From a physical point of view, how
Untitled
can I
Higgins
understand
gives,
this?
I was trying to, that's good, to reconstruct this in my mind. I know Untitled Higgins gives that, but I couldn't do it before. But I know he gives it. If I go back, I would say, oh, yes.
Okay.
Yeah. It has to do with the fact that as you drop the amplitude, the wave expands too. That is because this is a packet, so it expands the wave. As you drop the amplitude, it becomes flatter, and if you increase the amplitude, it becomes more steep. But you have to go there, and as I told you, it is there, but I can't right now.
okay, well, thank